It's Terry Dennery of the MathWorks. So anyways, we're going to start up where we finished last time, um, where we came up with this really good inverse mechanics shaft, and it's through this that we understood for a motion command what would be required of our motor with regard to providing torque to make the mechanical shaft move the way we want to. Okay. And anyways, it kind of comes down to, what are we actually, you know, actively capable of adjusting? Well, it's really voltage. And so it really comes down to how do we adjust the voltage so that we get the torque that will create the movement that we want? And that's what you'd call a torque controller. And we're going to use feedback to do this. And so we're going to compare kind of what we want with what we're observing and use that information through a PID algorithm to adjust that voltage and get the torque that we need. All right. So anyways, let's kind of get started on this. And so I'm going to delete all this stuff. I'll delete that scope. And I'll use that calculation to figure out that voltage to some degree, right? And so I'm going to move this up like right here, all right? Let's move it maybe a little bit further because we're going to need to add a little bit in between, right? So our commanded motion will imply a commanded torque, and we will compare that torque with what's being delivered to the mechanical shaft by our DC motor, right? The algorithm will be a PID, all right? And the PID will choose the voltage that we're going to apply to the motor, and it will do it with a little bit more. It needs a little bit more to do it, all right? So anyways, I'm going to type in SUM for the sum block. I'm going to put this in right here, right? Let's zoom in real close. And so instead of this being configured with a plus plus, I'll make it a plus minus. Let's hit the space bar, and basically through this we'll make a comparison between what we're commanding torque to be and what we're observing. The difference between the two will be presented to the PID. The PIDs, they're superb at driving errors to zero, or at least driving whatever's coming in, to go to zero, assuming that you're able to control something real that does have that kind of impact. Okay, and so let's kind of get into what I mean by that. Okay, right, so we'll just kind of observe the system through this angular velocity measurement. Well, let's just go ahead and hit run and kind of see how we do. Okay, so somebody put those markers back in there, so I'm gonna get rid of those. No, that's me. I don't know how I did that. So let's uh, choose none. Okay, apply. Okay, and from the previous video, I recall that velocity really does have this kind of parabolic shape, and so that's kind of good. But we really do want to check, and so what I'm going to do is take our commanded signal, and you'll recall that that's position, velocity, and acceleration, and all we really want is velocity to do the comparison here. And so this selector block is very useful at just picking off that second signal, which is the velocity. And so it's send it into that same scope and hit that. And let's look at how we did. And so it's kind of interesting that we were able to get the same shape. And again, PIDs are kind of cool what they can do, but it's not doing a great job yet, right? And so let's go into the PID block. Now again, PID, proportional integral derivative. It means that error signal coming into the PID block, that in this case, it's a voltage that is going to be identified that achieves our mission, that the voltage being delivered will be composed, of the sum of P times the error, Ki times the integral of that error with regard to time, and then Kd times the derivative of that error with regard to time, okay? And what those values should be, well, really depends on the thing that you're trying to control, right? And it's kind of cool how, like, let's put this like on screen so we can really see this, that It doesn't even really care about units that much. The all that stuff gets kind of worked out and incorporated into these, kind of um, identified parameters, right? Okay, let's move that back. All right. And what we're going to see is that the there's amazing capability that's been developed by controls engineers over the years, and things like analyzing a step response. And this is generally thought of as, hey, I want to command a step from 0 to 1, and I want to see what the response would be. All right. And there's things like Bodhi plots and root locus and all kinds of amazingly, useful tools that have been in the control system toolbox for quite some time. And we're kind of tapping into that because we're sitting on top of ultimately the calculation capability of the control system toolbox, right? And anyways, but by clicking on that tune button, it's saying, well, before we're getting the dash line with the values of 1, 1, and 0 for those three parameters. Now, if you switch it to 0, 120, and 0, which is really interesting that it's purely I, that you're going to get a better response, and that's what's showing up with the blue curve. And we look at these numbers down here, and it says, well, it looks pretty good. Rise time of 0.03 and so forth, and so I'm highly encouraged that this will be better, but it's always a good idea to try it out, right? And so I'm going to update my controller with these newly calculated gains, which we see right there, all right? And let's run it again. So certainly way, way better, okay? But I would argue that it still can be a little bit better than that. The whatever that algorithm thinks of as being good, I may not agree with. And I definitely want that blue curve on top of that yellow curve a little bit better, right? And so I'll simply go back into the PID block. Let's hit that tune button again. And it's kind of simple what I'm going to do here. I'm going to just ask for a faster response. So if you kind of look at where we're going from, if I click this right here, I'm good with robustness, and these are important terms, but I'll just kind of avoid the definition for right now. I'm going to make it a little bit faster, and so you'll see the blue curve is kind of where we're operating now, and you'll see things like rise time and settling time. They're quite a bit better. And with that, I will hit the update block one more time, or the update button. Okay, and again, I'm not asking for a step response. I'm asking for a very intended motion. Okay, and so with that, I'm pretty happy. Although, we're going to go on to some additional videos, and we'll study this a little bit more. And certainly, range of voltage operation, a number of things, will be considerations that we'll bring into this too. So anyways, thank you.